Okay, off we go. So, last time, here's what we were talking about. We've talked about double integrals. We talked about iterated integrals first, then double integrals. Then we came to the realization that you can use iterated integrals to compute double integrals, and strategy for solving problems ensues. Okay, so how do you know which way to slice? We've addressed that two different ways. Let's see, we made the observation last time that you can look and see, wait a second, which variable would you prefer to solve for? Much rather, in this case, solve for y instead of x. I don't like square roots, right? So, if you want to solve for y, great. Put it on the inside where that's what you will therefore need to solve for, right? Whereas, if you make the mistake of saying, hey, I want to solve for x, you put the dx on the inside. And then again, bad bounds result. Okay, so that's the first lesson. Think about which variable you'd rather solve for. Second lesson, this is again where we were last time. Try to avoid slicing in such a way that will sort of force you into writing down multiple iterated integrals. No one would rather do, well, let's not be too broad, but in general, I mean, broadly speaking, if you have a choice between one integral or two integrals, right, probably want to go with one, all else being equal. So we talked last time about how to see these details as I've got written, and what I'd like to start with now is how do we see this coming in advance? Right? So, I can see I'd much rather do the first option than the second option, but I'd rather not have to write them both down. I'd rather just kind of go straight to the best option every time. So here's my take. My take is that the problem happened because the point determining the upper bound for that inside dy integral and the point that determines the upper bound for that dy integral, that point jumped from one curve to another curve. That's kind of what happened there, right? We get two different bounds because their points come from two different curves. This point could jump from one to the other because the curves intersected. The curves intersect, typically making a corner. So, with this in mind, here's my suggestion, and this works really well, I think. And that is, think about it as you're slicing, right? So here we are trying to figure out how to do our dx slicing on the outside, going in this direction. Of course, our slices look like this. This is our dx slices proceeding along. Try not to slice through a corner, right? You can see it's because I sliced through that corner right there. That's why I have to stop the 0 to 1 dx integral. Start a whole new integral going this way, right, where x goes from 1 to 2. Does that make sense to everybody? Okay, so try not to slice through a corner. I'll rephrase that as every time you slice through a corner, you're going to have to stop the integral you were working on and start a whole brand new integral. Now, just for comparison purposes, let's think about how that applies here. I claim here we don't have any issue at all. Let's think about the slicing process. Now, obviously, of course, we have a corner there, we have a corner there, we have a corner there, and as I go in the y direction, going that way, my slices, okay, well, wait a second now. Our very first slice slices through a corner. Well, that's okay. I wasn't working on an integral. I'm happy to end the integral that I wasn't even doing. Right? So that's not a problem. I'm going to have to start a new integral. Cool, I was going to start a new integral there anyway. No problem at all. Right? So, fine at the start. And then likewise, slicing along, no corners. We slice through a corner at the end. Again, fine, I was going to end the integral there anyway. Right? So don't worry about the start and the end. But in the middle of your slicing process, you don't want to slice through corners. And trying to get that, there we go. Starting and ending aside, slicing dy on the outside doesn't slice through any corners. Okay, how we doing? Everybody see the takeaway there? So these are a couple of really good little sort of, bits of strategy, insights to help you avoid effort. Try not to slice through corners. Try to arrange your differentials so that you solve for what you want to solve for, and avoid having to solve for what you don't want to have to solve for. By the way, good news, side note, these two strategies, in the great majority of cases, will suggest the same order of the differentials. Right? That said, that's when they meaningfully suggest one side versus the other. Notice, this first example that we did, if I took the don't slice through corners strategy, doesn't matter. So the corners point of view does not help with this one. And likewise, which variable would be hardest or easiest to solve for doesn't really help with this one. It's just straight lines. That's all easy. Right? So you need both points of view to address different kinds of situations. Okay, moving along. Sometimes you have to find the domain. Let me go ahead and go full screen here. Sometimes the domain is not explicitly given. There's two interesting things about this example. Let's just dive in. We have given this plane and this, that's not a plane. I got ahead of myself. This paraboloid, colors, this paraboloid, and this plane, I think I got it right finally. And we're looking for the volume in between, and of course that's what I have in gray, now purple. Cool. All right, well, how are we going to find the volume, blah, blah, blah? Well, double integrals can help us compute volume sometimes. So it'd be nice to do this with a double integral over what? There's no domain given. So in a situation like this where there is no domain explicitly given, what you're going to want to do is think about, okay, how would I slice this up? And as I slice this up in a way that seems natural, what can I call the domain that gets sliced up exactly correspondingly to what I'm actually interested in? So in particular, I'm going to suggest that we take this three-dimensional solid and we do vertical slicing in both directions, right? Sort of in the x, in the YZ direction and in the XZ direction. Right? Slice it up to make a bunch of, again, I like to call them French fries, right? And as I do that, notice every French fry has a corresponding little shadow down there in the XY plane. So if I want to add up all the French fries, I'm going to have to add up all the shadows. Now, overall then, if I'm interested in all of the French fries, then I effectively am interested in the entire shadow. And so it's very convenient then to use the shadow as my domain. If I use this entire shadow as the domain, then in fact, perfectly fair to say that every little piece of the domain, I draw it sort of cartoonishly big here just for visibility reasons, every little piece of the domain corresponds to a piece of the volume that I'm interested in. Is that cool? All right, now, another thing students very often get stuck on, again, it's very common for students to think of single variable integrals as area under a curve, area under the graph curve. And likewise, despite my advice, to think of double integrals as telling you the volume under a graph surface. This is a volume, but it is not a volume under a graph surface, right? The volume doesn't go all the way down to the XY plane, right? So, can we do this, right? Reason number, I've lost track of why we should not think about double integrals as volume under a graph. It's very constraining, it's very limiting, right? I'm going to remind you a much better way to think about double integrals, right, is a way of adding stuff up. Right? So think of it as, in the same way that you can think of a single variable integral as, look, we're going to look at little subintervals one at a time, and on each subinterval, for whatever reason appropriate to the actual question, On each subinterval, we're going to multiply the length of that subinterval times some function. Why we multiply by that function? Well, we tailor it to the circumstance. If we're interested in computing an area, this would be a height times a length. If we're interested in computing mass, then this would be mass per unit length times a length. Always something times size. So likewise for double integrals, right? I propose is the best way to think about double integrals. Forget about volume under a graph. Again, very narrow. Think of it as, for whatever reason, you have a domain, you're going to chop it up into little sub-rectangles, on each of which, for whatever reason appropriate to the circumstance, you're going to multiply the area times some function. Right? Now, if you're interested in mass, this is mass per unit area times area. If you're interested in computing a volume, this would be a height times an area. Right? We don't have to say graph. There's nothing about a graph that's necessary to talk about volume being height times area. So with that in mind, in fact, we are interested in a volume, and furthermore, on any given little piece, let me zoom in here, on any given little piece, what would I multiply? Let's see here, color choices. What would I multiply by this area to get this volume? And in fact, it would be, I wanted the pencil, sorry. It would be that height. Right, this value of z at that point minus this value of z at that point. Height times area gives you volume. No reference to graphs. Don't need any graphs. Don't actually even really particularly want to view any of these surfaces as graphs. What do you think? Everybody buying it? Okay. So thus this result here, height times the area of the piece of our newly defined domain. Okay, so next thing to talk about is how do we actually get our hands on what that domain actually is? And this is again a little bit tricky. It's all well and good to say it's that shadow. There it is, that shadow. How do we find that shadow? I need algebra, not words, to describe this domain. Okay, here's how we're going to do it. I'm going to start with an observation that wherever you are in the domain, the height up to the paraboloid, here's my paraboloid, the height up to the paraboloid is that value of z right there. And from that same point, the height up to the plane is that z right there. Now that's in the domain. On the boundary of the domain, it's going to be a little bit different. On the boundary of the domain, the height up to the paraboloid and the height up to the plane are the same. Same height. Right? That's because on the boundary of the domain, the boundary of the shadow, again, geometric appeal. You look at the picture, the boundary of the shadow is going to come from this edge, as it were, of this solid. Is that cool? Geometric appeal. Does everybody see that? So that's the answer then. What we're going to do, we're going to identify where the edge of our domain is by just insisting that z and this z must be the same, and that gives us the following equation, insisting that the two z's be equal, gives us this right here. And notice a little bit of algebra was necessary to make that make sense. I mean, the green z I've got a formula for, x squared plus y squared. Boom, there it is. This z, I don't immediately have a formula for it. Got to do a little bit of algebra, a little bit of legwork, right? And you solve for that z and you get this. Everybody happy? Okay. Now, I do want to point out one thing. There is an opportunity to mess up pretty severely here. And I see the following semi-regularly. Less now that I've been making a big deal out of it, right? So that's why I do these things. But a lot of students reason as follows. They say, well, I want to find where the two surfaces intersect. That's true. The two surfaces are described by equations. Also true. And if I want to know where the two equations are both satisfied, then I will think carefully about the following phrase. I will set the equations equal to each other. I don't know if y'all have heard this one. It's nonsense. It doesn't make any sense at all. But I see this, right? Students will say, oh, okay, I'm going to choose to set this equal to this. Doesn't make any sense at all. Right? Might as well set z equal to 7. That's also wrong, right? Doesn't make any sense. And just for the funny of it, let me just point out, all right, here's an equation. Here's another equation. If I want these to both be true at the same time, do I need 3 to equal to 7? No, not at all. Total nonsense. Does that make sense? Everybody see why this is it just doesn't make any sense, right? It's one of these things that feels like it ought to make sense, but it just 100% doesn't. Yes.
Could you use one of the other variables, like solve for x on both sides and then set what's left over equal to each other?
I hear you. It depends on the geometry of your shape, right? So what's nice about this shape is that when I project it down to the XY plane, I'm going to get what I call a simple picture, right? If you were to say, look, I'm going to let one Y equal to another Y, what you'd be saying is that you have two different functions where Y is a function of X and Z. That's not really true. See what I'm saying? You can't really solve for Y. You don't have Y as a function of X and Z. You can also see if you were to try to project into the XZ plane, all sorts of bad things happen. The edge of the projection doesn't come from the edge of, the two surfaces intersect. You'd have to worry about what I might call horizon lines on the side. It just turns into a nightmare. So it's not that you can't, it's that in this circumstance, I think it would be highly undesirable. Yeah. But as a broad rule, you should always think about what's going to make your life the easiest. And it will not always be the Z. Absolutely. Great question. Anybody else? Okay. And then while we're here, I'm going to recognize real quick that here again, got to complete the square sometimes. Right? Completing the square is what turns an equation that we don't recognize the form of into an equation that we totally recognize. Weird though that radius is going to be, this is just the equation of a circle. Everybody happy? All right. Okay, so that does it for 5.2. 5.3 is an oddly short section. The textbook that we're using does not follow any constraints on how big sections need to be. Sometimes they're minuscule. 5.3 is teeny tiny, and then 5.5 is a giant, and 7.3 is a super giant. So anyway, kind of weird, but 5.3 is very, very quick. This is just about changing the order of integration. If you have an integral that's dx dy, why would you and how would you change that to an integral dy dx? Right. Now, one thing we've talked about, you can't do this. Right, this move right here where you switch the differentials, you switch the bounds, and everything just works. Rectangles only. This only works for rectangles exclusively. So there's going to be more work involved here. But it's pretty straightforward. I think a single example should do it. So here we go. Here's an iterated integral. By the way, why would I want to switch the order? of the differentials? Well, if you look at this inside integral, that inside integral requires an antiderivative that we can't compute. To be clear, it does have an antiderivative. It just doesn't have an antiderivative that you can write down with regular functions like exponentials and polynomials and stuff like that. It's too terrible of a function. Okay. So we want to switch the order of differentials because we're at a dead end and we have no other options, and we figure maybe if we backtrack and take a different road, maybe it'll get us where we want to go. Okay, so all you got to do is just undo the usual process that we usually do. I'm just going to try to get everything to fit on the screen here reasonably. Yeah, I think I can. Yeah, there we go. Okay, so apparently we start at y equals 0. Okay, I can do better than that. Apparently we start at y equals 0, so we draw the line y equals 0. Apparently it ends at y equals 1. Cool. For any given value of y, so we're going to look now at some value of y between 0 and 1. Apparently, we're going to be starting where x equals y, which is a point on that curve. And we're going to be ending where x equals 1, which is a point on that curve. So between y equals 0 and y equals 1, for every value of y between 0 and 1, we're going to go from there to there. And I think it's a pretty easy pitch then that our area for our domain is that triangle. Everybody see the process? We're very much just kind of reverse engineering the process of turning a double integral into an iterated integral, just going backwards through that process. Is that cool? Okay, again, why are we doing this? Well, lack of options, right? I was looking at looking at this iterated integral up here, dead in the water, can't proceed. We've now rewritten it as a double integral. That double integral I can then slice the other way. Now, I'll let y'all think that through. But this, when you slice it up dy dx, you get these bounds. Make sure you can do that, obviously. And here we are again, e to the x squared in the integrand, iterated integral. This is where we ran into a roadblock last time. A little bit scared that we're going to have another roadblock here. See what happens. Starting with the inside, as we must. The key point, x is now the outside variable. That means x is a constant. That means e to the x squared is a constant. Constants just come along for the ride. This is an easy antiderivative to do. Just y, e to the x squared. Plug in these values. This is how that inside integrand. This is how that inside integral works out. Now, okay, so you say, yeah, no problem. So what are we going to do about the dx integral? The dx integral was the problem in the first place. So here we are again, ugly function of x, dx. How are we going to deal? And the answer is, thankfully, we now have an extra factor of x there. So it's still a scary looking integral at first glance, but this is a scary one that works out pretty easily, as opposed to a scary one that is not positive. And so, yeah, you do a u substitution, u equals x squared, details, y'all know single variable calculus. Works out great. Everybody happy? Okay. So, these are fairly rare circumstances, but every so often, so for those situations, this is how you do it. Okay, honestly, I feel like this could have been an example in section 5.2. But it is section 5.3, and we are now done with 5.3. So moving along to 5.4. Yeah, triple integrals. Here's the big idea. Sometimes we're chopping up and adding up, not over an interval, not over an area. Sometimes we're doing it over a three-dimensional region. So let me just remind you, our strategy for that, chopping up and adding up, this is several pages back when we were first defining double integrals, and we made the observation that if you have an interval, you chop it up into little pieces, make an argument on each little piece appropriate to the circumstance, and you get a Riemann sum. Right? Where on each little piece, such as a sub-interval there, you write down that. Something times length. Let's see, for a double integral, we just extended and said, well, look, sometimes you have an area, not an interval. And in those cases, we get a double integral. If I chop up that area into pieces and answer the question on each little piece, right, keeping in mind that on a little piece here, this is a piece of area, and so we're going to be multiplying something times area. Usually a density. Usually stuff per unit area is what you're going to want to multiply by area. Just like over here, it's usually stuff per unit length that you want to multiply by length. So this strategy, I mean, again, arguably kind of the same strategy in both cases. It's just the dimensions are different. A couple of details are different. Basically the same strategy, chop it up and add it up, right? The three-dimensional version of that also makes sense. Sometimes you have a three-dimensional solid. Let's see here. Colors, yeah. And just to get the ball rolling, let's pretend this is like an aquarium. All right, maybe I want to compute how much pollution there is in my aquarium, and for whatever reason, I have reason to believe that the pollution concentration, pollution per unit volume, is some known function. How do I compute the total amount of pollution? Well, I would look at each little piece. Each little piece. Now, this is not a length. This is not an area. This is now a volume, right? This is not a sub-interval. It's not a sub-rectangle. I'm just going to call it a sub-box, right? And on that little piece of volume, for whatever reason appropriate to the question, I'm going to multiply something times volume. And again, let's go back to our pollution metaphor. If I want to know how much pollution there is in this little box, if I know pollution per unit volume, that's what you multiply by volume. This would then tell me pollution, and I would add that up to get the total amount of pollution. Everybody happy? The same basic idea. It's just further extending what we've done. By the way, we're not going to do the following in this class, but if the situation should ever arise where you have not one, not two, not three, but a four-dimensional domain, it's a scary thought, isn't it? If you have a four-dimensional domain, you could probably guess, what you're going to write down as a quadruple integral. And there are circumstances where that comes up. I took a sophomore physics class. Well, part of my physics major. But anyway, when I took a sophomore physics class, we had to do an integral that involved probability. Probabilities are computed as integrals sometimes, and the domain for the integral was in what's called phase space, which is not physical space, but it's just kind of an abstract collection of conditions that can come up. And I had to do an integral on a six-dimensional phase space. It's just like this. Just six-dimensional size instead of three-dimensional size. All the same basic ideas. Okay. Alrighty. Okay, so nice starter example, and kind of my favorite starter example for integrals. Y'all have heard me say it a bunch of times. I don't really like the idea of thinking of integrals in terms of graphs. It's It's convenient when you get started, but it's very limiting in the long run. Right, most of the time, you just don't need to know the area under a curve, the area under a graph curve. It's a fairly rare application. Fairly rare to need the volume under a graph surface. It just doesn't come up that much. Usually, you're computing stuff of some sort of accumulating quantity. So mass is really nice because while it is stuff, right, we're not constraining ourselves to graphs. It is nevertheless a stuff that's kind of physical and relatable, right? And so it's less abstract. So, okay, so how are we going to compute mass distributed over some sort of a volume? Well, the first thing I write down is that mass is an accumulating quantity. The whole of the mass is the sum of the little pieces of mass. Integral shorthand, right? But sort of a recognition that this is an accumulating quantity. And then on each little piece, it is a pretty reasonable proposal that mass is mass per unit volume, which was given, times volume. And lo and behold, boom, I have myself a triple integral. Still don't know how to compute it, but nevertheless, once I can figure out how to compute triple integrals, this triple integral will tell me whatever mass I'm interested in. Is everybody on board so far? All right, now before we get to the computations, I think it's really important to talk about how we think about this, and I know I say the following a lot, and I just got through saying it once already. Here it is again. The first point of view that almost everybody sees for single variable integrals, area under a graph curve. And it has its moments. As y'all know, I push and prefer this point of view on single variable integrals because this is a focus on sort of the broader idea of adding up a bunch of stuff. Right now I say mass, again, it's physically relatable, but whatever, any sort of accumulating quantity, whatever it might be, and an integral is a way of chopping stuff up into pieces and looking at one piece at a time and adding them up. Okay, double integrals, same story, you've heard it before. You can think of it as volume under a graph surface. Again, I'm not a huge fan, but instead, we can think of it as a sort of an accumulation. Stuff now distributed over a two-dimensional region. Okay, so pros and cons, and different people have their different takes. Here's where it gets, I think, very clear why I like my way better, at least, and maybe I shouldn't overstate it, but I really like my way better. What would be the analogous take for a triple integral? Well, we've got a problem because a single variable integral gives me a two-dimensional picture. Double integral gives me a three-dimensional picture. You should expect a triple integral to give you a four-dimensional picture. And in fact, look at my integrand. My integrand's a function of three variables. If I have a function of three variables and I look at its graph, now there's four variables. This is a four-dimensional picture. And you can't visualize that. If you think you can, I don't believe you. Right? Does that make sense to everybody? It's a real problem. That's a nasty... we've got a pattern that we need to understand that we absolutely can't. So, all right. Whereas, let's look at this alternative point of view that I've been pitching. No problem. Right? If we're viewing a single variable integral with a one-dimensional picture, double integral with a two-dimensional picture, and then I ask, how am I going to understand a triple integral? Well, it's a three-dimensional picture. Here it is. Fine. No problem. Perfectly intuitive. Everybody see the pattern there? Now, again, there's different reasons, pros, cons, and don't get me, I'm not saying that you should try to, memory hole these points of view, right? I mean, they have their moments, I suppose. It's kind of nice. I've used this point of view, this idea of thinking of a double integral as volume under a graph, to provide some intuition for why double integrals can be computed with iterated integrals. That was cool. That's valuable. I like that. So it has its moments, right? But day in and day out, most of the time, I want to encourage thinking of single variable integrals as an accumulation over a one-dimensional domain. Double integrals, two-dimensional, triple integrals, three-dimensional. Okay. By the way, just a warning. That's a wrong word. Here's an observation I've made over the years. I've noticed that some students will choose to think of single variable integrals this way, double integrals this way, and triple integrals that way. Now, let's think about that situation, right? If this were you, if you were going to think about triple integrals, let's see here, the triple integral with a three-dimensional picture and double integrals with a three-dimensional picture, you can see you would have a natural opportunity to confuse these, right? And I've had students ask many times, hey, this is a three-dimensional thing. Sometimes you compute three-dimensional things with double integrals and sometimes with triple integrals, and why is that? Right? And well, the answer is because you're conflating two qualitatively different kinds of pictures, right? And it's just it's the cost of choosing an inconsistent set of perspectives. So anyway, I'm not telling you what you can and can't do, but if you do choose these red check marks, then you've got an issue that's going to have to be worked out. Okay, enough of that. Some good news. Let's see here. Let me stay back here for a quick second. Again, I did use this picture to explain why double integrals can be computed with iterated integrals. And that was a nice argument. I find it intuitively satisfying. I find it comforting. If I were going to give you an analogous argument as to why triple integrals can be computed with iterated integrals, I would have to use a four-dimensional picture, which I can't, right? So I'm not going to be able to give you that intuition. What I'm going to do is assert, hopefully you believe me, that while this geometric argument is satisfying, it's not the only such argument. There is a purely algebraic such argument that you don't need a picture, it doesn't invoke graphs, it's purely just looking at the Riemann sum definition of a double integral and playing some delicate and dangerous games with moving limits in and outs of summations, and it gets subtle and deep. And it can be done, and it's not appropriate for this class, in my opinion. So I'm just not going to give you the argument, but the argument is certainly there, and the conclusion is certainly true. So triple integrals, absolutely, no problem, can be computed with iterated integrals. Perfectly fine. And furthermore, take your pick of any of the 6 possible iterated integrals. And let's just think about that for a second. You do, in fact, have 3 differentials, and there's altogether 6 different ways to, think through those 6 different combinations, right? But there are 6 different ways that you can order those differentials, and so therefore 6 different iterated integrals. Okay. All right, so this is our punchline. This is our sort of general strategy for how to compute questions where there's an accumulation happening over a 3-dimensional solid domain. It's hopefully familiar looking, right? The missing piece is we no longer have anything here. This is what was 3-dimensional volume. Now this would have to be 4-dimensional, whatever that notion of size is, right? I don't know what to call that. So sure, we don't have that. We didn't really need that anyway, right? So by the way, yet another really good reason to not hang your hat on this kind of a point of view. You wouldn't be able to solve application problems. What we're going to do instead is we're going to turn application questions into triple integrals we're going to recognize that triple integrals can be computed with iterated integrals, and then we're going to compute the corresponding iterated integrals. The same three-step process we did before. It's really, really similar, just 3 instead of 2. Okay, so let's see that in action. Here we go. We're going to compute a mass over a solid. Now, we've already made the case that mass is a triple integral of density. Density is given. So we've already done, phase 1 of the question we've already got done. Phase 2, we just talked about. Yes, you can turn triple integrals into iterated integrals. Now let's talk about the bounds. Hopefully no surprise here, but notice that the bounds for the dy integral is the range of values for y on our domain. It's exactly what you would expect. Notice that the bounds for the dx integral are exactly the range of values of x for our domain. And you can see this coming, the range of values, the bounds, I should say, for the dz integral is the range of values for z on our domain. Right, so exactly what you would expect and hope. Buying it? Everybody happy? Okay. All right. It's just like with iterated integrals with, when you have 2 of them. It's just that now there's 3 of them. Integrals on the inside have to be done first. You have to work inside out. And variables that are further to the outside, you treat them as constants. In fact, they are literally constants, and I'll draw a picture to motivate that on the next page if I remember correctly. So anyway, let's take these one at a time. Well, I'll do the first one anyway. Here's our inside most integral. Notice, in fact, let me zoom in for focus. If I can get this to cooperate. There we go. Notice x and y are my variables on the outside. That means x and y are constants. Constants, of course, just kind of come along for the ride. And so when it comes to the actual integration here, actually doing the dz integral here, well, 2z is what's going on with that term, and the antiderivative with respect to z of 2z is z squared. All right, so remember now, this is part of your job. Anyone who's evaluating an iterated integral of whatever size, whatever dimension, you got to keep track of which variables are playing what role at whatever stage of the calculation you're at. Right, so for the dz integral, for the inside integral, x and y are constants. I treat them as constants. Everybody happy? Student asked me in the earlier class, okay, what do you do with z for the dx integral? Well, the dx integral, you'll notice, doesn't have any z's in it. The z's have integrated out, as they must. But the y is still on the outside, still to be treated as a constant. Right, and so, et cetera, et cetera. Everybody happy? Okay, so let's see here, moving along. Non-rectangular domains. All right, this is where things started getting geometrically tricky when we were looking at double integrals, and we had to think about, okay, how do we approach a non-rectangular domain, and how do we visualize? I'm going to flip back to where we were on that. Let's see here. Here. Right? And so we revisited the question of volume under a graph. Again, it has its moments, right? It's useful sometimes. So we noticed that the process is almost exactly the same, even when the domain's not a rectangle. Very little difference. There's only one little teeny tiny itty bitty little difference. The only difference is that the inside bounds are now functions of the outside variable. That's it. Everything else is the same. Right? And we also noticed we don't even need the three-dimensional picture. If that's the only thing we have to keep track of, I just have to figure out what are these inner bounds as functions. The integrand's the integrand. There's nothing to talk about with the integrand. It is what it is. If you only need to figure out the bounds are entirely determined by, should have erased that, by the domain. So you don't need to draw the big picture. You can just draw just the domain itself. And we argued as follows, that the outside bounds are usually pretty straightforward. You look at the lowest possible value, the highest possible value, and then you fix and say, for a given value of y, and now we focus purely and only on that one given value of y. We are, after all, just moving along here like this. We are, after all, only looking at this one, right? This one little slice of bread here. Right? I don't care about what's going on over here. Well, that's part of a different slice of bread. We'll get there. Right? I don't care what's going on over here. One slice at a time. Therefore, looking at only one y cross section of the domain at a time, and then we say wherever your cross section starts is going to tell you your lower bound, and wherever your cross section ends, that's going to tell you your upper bound. Cool. So you identify the range of values for one of the variables, then you fix that variable. You look only at that cross-section indicated by that fixed value of that variable. And looking only at that cross-section, you then move on and ask what's the bounds for the next variable. And it's thankfully exactly the same process for triple integrals. And I think this is easiest to see just by an actual geometric example. So let's do this real quick, and we'll call it a day. Call it a week. I made up some random solid, whatever, non-rectangular. Arbitrarily, I'm going to do my slicing in this order right here. Doesn't matter, 6 different options. This is I got to pick one so we can actually do it. Starting, therefore, with x, we're going to look at our solid here and ask where is the lowest value of x, and I argue that the backmost point on our solid, that's going to give us our lower bound, right? And then the frontmost point is going to give us our upper bound. And there you go. There's the outside bounds, least and greatest. Cool, is that right with me? Then, following the pattern, just like we were talking about previously, we then fix a value of x. We got the range of values for x. We fix one. We now focus our attention only on that cross section. Now this is geometrically different because now we're starting with a three-dimensional solid, a x cross section of a three-dimensional solid. Now it's not just an interval. Now it's an area. But just like before, we fix that. We look only at that cross section. Forget about what's over here. We'll get to the stuff over here. We'll get to that for other values of x. Forget about what's over here. We'll get to that for a different value of x. Only for that value of x, we now ask the next question. Okay, what's the range of values for y? And well, y slices, for any given value of y slices are going to look kind of like this. Right? And the very first, let's see, how do I do this? Let me get rid of that. There we go. The very first y slice will give you your lower bound for y, and your very last y slice will give you your upper bound for y. Same pattern, just, one higher dimension. Everybody happy so far? We got one last little teeny tiny little bit. Is that everybody with me? The last little bit is to recognize that, well, okay, now I've got two variables to fix. So I can't just say x and only x is fixed. Now I got to fix both x and y. And when you fix both x and y, you're basically fixing a point down here in the xy plane. You're looking only then above that point in the xy plane. You might say you're looking at this y slice of our x slice. It's a slice of a slice. It's geometrically challenging, right? It's hard to visualize. On that slice, lower bound comes from the lowest point, upper bound comes from the upper point, and there you go. Now we've turned a triple integral into an iterated integral. This is a great place to draw the line. We'll pick up here after break. Y'all have a great break. See you on Wednesday.